Let us start module 3 of chapter 5. In this module, we will study Alexander's subbase theorem. So, before stating the Alexander subbase theorem, let us recall the notion of subbase for some topological space. Let us recall the real line with usual topology. Now, if we consider the open rays of the real line, then taking all possible finite intersection of these open rays, we get the collection of all open intervals, and from these open intervals we can generate the topology of R. In fact, to describe the topology of R, it is sufficient to consider the open intervals. But it is not necessarily true in every case that open rays will speak everything about the topology of R. We have observed in all cases that every theorem of topology, it is sufficient to consider bases. For example, for compactness, it is sufficient to prove that every open cover by basis elements has a finite subcover. Though in the original definition of compactness, we know that the definition runs as follows: if every open cover has a finite subcover, then the topological space is compact. It can be replaced, the open sets, by basic open sets also. The beauty of Alexander's subbase theorem is that here we can replace basic open sets by subbasic open sets. That means Alexander's subbase theorem says that every open cover of X by subbasic elements has a finite subcover, then X is compact. Throughout this module, we will study this theorem. Let us pass to the module presentation. As we have discussed in the elementary discussion that for describing compactness, it is sufficient to consider basic open sets. That means we can say the following theorem: let X tau be a topological space with a base script B, then the followings are equivalent. Every open cover has a finite subcover if and only if every basic open cover has a finite subcover. That means this shows that open sets can be replaced by basic open sets. As I have already mentioned that finally we shall prove that every open set can be replaced by subbasic open sets also. So, let us start with the definition of subbase. Let X tau be a topological space. A subbase for this space is a collection B of subsets of X such that tau is the smallest topology that makes each member of script B is open. Elements of script B are referred to as subbasic open sets. Taking all possible finite intersection of subbasic open sets, we get the collection of basic open sets. Now, we can observe that to test the convergency in a topological space, subbasic open sets are sufficient. That means, in a topological space X, of course we shall consider the topological space X as Hausdorff space, that is, in a Hausdorff topological space X, a sequence Xn converges to a limit X if and only if every subbasic open neighborhood of X contains Xn for all but finitely many Xn's. We know this is clearly true for basic open sets, but it is possible to prove that this is also true for subbasic open sets also. The one part, necessity part, is obvious. For the sufficiency part, let B be an open set containing X, and we have given that every subbasic open set containing X contains all but finitely many elements of Xn. Now, since B is a basis element, there exist subbasic elements S1, S2, Sn such that B is equal to intersection of Si, I runs from 1 to n, and X belongs to each Si. Now, for each I, we can find some Ni such that X in I belongs to Si for all n greater or equal to Ni. Now, let us take N0 as maximum of Ni's. Then clearly Xn belongs to intersection of Si, I runs from 1 to n, for all n greater or equal to N0. That means Xn converges to X. So, this result shows that to test the convergency, it is sufficient to take subbasic open sets, but not every topological aspect, not for every topological aspect subbasic open sets are sufficient. For example, we know that a point X in a topological space X is a limit point of a set E if and only if any basic open set containing small x meets the set E in infinitely many points. But the claim fails for subbasic open sets. For example, let us consider the set Z in R. Then, if we consider the point 0, then we can observe that every subbasic open set containing 0 meet Z, but 0 is not a limit point of Z, or if we take any real number R, then any subbasic open set containing that real number meet Z in infinitely many points, though no real number is a limit point of Z. Again, in the case of continuity, we are lucky. We can show that continuity can be explained in terms of subbasic open sets, because continuous functions, inverse of continuous functions behaves well. In fact, a function f is continuous if and only if for every basic open set its inverse image is open set. It can be easily proved that a function is continuous if and only if for every subbasic open set its inverse image is open. So, now let us state our coveted statement of Alexander subbase theorem. Let X tau be a topological space with a subbase script B, then the following conditions are equivalent. Every open cover has a finite subcover if and only if every subbasic open cover has a finite subcover. We can apply this theorem to prove that any closed interval, closed and bounded interval in R is compact. If we assume this theorem, we do not require Hehn-Borel theorem or Bolzano-Weierstrass theorem to prove that closed and bounded intervals in R are compact sets. So, let us come to the proof of Alexander subbase theorem. To prove this, it is sufficient to show that if every subbasic open cover has a finite subcover, then every basic open cover has a finite subcover, because we have already mentioned that if every open cover has a finite subcover, then every open cover by basic elements has a finite subcover and vice versa. That is, compactness is equivalent to saying that every basic open cover has finite subcover. Now, suppose for contradiction that every subbasic open cover has a finite subcover, but at least one basic open cover has no finite subcover. Let us call those basic open cover which has no finite subcover as bad cover. Now, if we order the bad basic open covers by set inclusion, then it becomes a partially ordered set. Now, let us consider a chain of bad basic open covers. Then their union is again a bad basic open cover. That means that is the maximal element of that chain. In this situation, we can apply Jones' lemma, and applying Jones' lemma, we can claim that there exists a maximal bad basic open cover. Say C is equal to U alpha such that alpha belongs to gamma and index set. That means if we extend C, then that will not be again a bad basic open cover. Thus, we can say that script C has no finite subcover, but as I already mentioned, if one adds any new basic open set to this cover, then there must now be a finite subcover. Let us pick a basic open set U alpha from this cover script C. Now, since U alpha is basic open set, there exist subbasic open sets B1, B2, Bk such that U alpha is equal to intersection of Bi, I runs from 1 to k. We claim that at least one of the Bi's also lie in the cover C. To see this, suppose for contradiction that none of B1, B2, Bk were in C, then adding any of bi to C, we can enlarge C so that this enlargement has a finite subcover. Thus, bi together with finitely many sets from C cover X, or equivalently that one can cover X minus bi by finitely many sets from C. Thus, one can also cover X minus u alpha is equal to union X minus bi, I runs from 1 to k, with finitely many sets from C, and thus X itself can be covered by finitely many sets from C, which is a contradiction to the fact that C is a bad basic open cover. Hence, one of bi's belongs to C. Let it be B1. From the above discussion and the axiom of choice, we see that each basic set u alpha in C, there exists a subbasic set B alpha containing u alpha that also lies in C. Since u alpha cover X, then B alpha do also. By hypothesis, a finite number of B alpha can cover X, as we have considered that every subbasic open cover has a finite subcover, and so C is good, which gives the desired contradiction. Hence, we have proved the Alexander subbase theorem. So, we have proved Alexander subbase theorem, which says that a topological space is compact if and only if every open cover has a finite subcover. Here we have used the original method by Alexandrov. The theorem is known by the name of Alexandrov. We can prove this theorem by using filter method also. We have already mentioned that by a filter we mean a collection of subsets which has finite intersection property, which does not contain any empty set and which is closed under the formation of supersets. We also know that by applying Jones lemma, every filter can be extended to a unique ultrafilter. We can use the property of ultrafilter rather than convergency property of ultrafilter to prove the Alexander subbase theorem. Let us go to slide presentation. So, now my target is to prove Alexander subbasic theorem by using ultrafilter. Let us recall that a characteristic property of ultrafilter is that if A is a non-empty subset of X and script u is an ultrafilter on X, then either A belongs to script u or X minus A belongs to script u. We also recall that an ultrafilter script u in a topological space X converges to a point X if the neighborhood system of the point X is contained in script u. In fact, in topological spaces which are not first countable, sequence are not enough. That means convergency are not enough to describe the topology, but ultrafilters, convergency of ultrafilters are enough to describe the topology. So, using the convergency of ultrafilter, we can prove the Alexander subbase theorem. Let X tau be a topological space, then the following conditions are equivalent. 1. X is compact. Number 2, any cover script S of S by subbasic open sets has a finite subcover, and number 3, every ultrafilter in X is convergent. 1 imply 2 is obvious, because if X is compact, then every open cover that may be subbasic or basic or any open cover has a finite subcover. So, we shall prove that 2 imply 3. So, let us assume that in X every subbasic open cover has a finite subcover, and let script U be an ultrafilter on X. If possible, let script U is not convergent. That means there exists no point of X to which script 2 converges. It follows that for each X belongs to X, one can find at least one neighborhood of X from script S such that Sx does not belongs to script U. To say it more clearly, it says that for every X belongs to X, there exists a subbasic neighborhood of X, say Sx, such that Sx does not belongs to U. Now, using property 2, we can say that there exist finitely many points x1, x2, xn belongs to X such that X is equal to union of Sx1, Sx2 up to Sxn, as Sx such that X belongs to capital X becomes an open cover of X. Since Sxp does not belongs to U, for any I is equal to 1 to n, it means that X minus Sxp belongs to U for every p is equal to 1 to n. This comes from the characteristic property of ultrafilter. Then using above equality, we get that U contains the union of the form X minus Sx1 union X minus Sx2 up to union X minus Xp, which is empty set. So, we get an empty set is contained in the ultrafilter script U, which is a contradiction. Therefore, we have that 2 implies 3. Now, to prove that 3 imply 1, suppose X is not compact, whereas every ultrafilter on X is convergent to a point of x. Since x is not compact, then there exists an open cover of x, say ui, which has no finite subcover. Therefore, intersection of x minus ui is empty, but no finite sub intersection is empty. Then x minus ui such that I has the finite intersection property. So, we can take an ultrafilter script f containing this. In fact, we know that every collection of sets with finite intersection property can be extended to a filter, and that can be extended to an ultrafilter. Now, for any point y belongs to capital Y is contained in some ui, and ui does not belongs to f, since x minus ui belongs to f. So, y is not a limit point of script f. This completes the proof of the theorem. So, in this module we have presented two proofs of Alexander-Sabbes theorem. One is the original proof due to Alexandrov, and another is using filter approach. With this we end this module. Let us pass to another module.